All right, let's go ahead and get started. Does anybody have any questions about anything before we jump back in? All right, so just to recap from last time, we're talking about basically how to find area. And the approach that we introduced last time was basically taking the area underneath some curve over some interval and basically representing it as a series of rectangles all having the same width. So we did this with this parabola on the interval from 0 to 1, and we found this area of 15 over 32. What do we think about that number we came up with? It's an overestimate, right? Why do we know that?
We're taking the whole area of rectangles that are also above the line.
Right. So, you know, if I want to find the blue area, I've done that, but I've also found, you know, all of this stuff as well. So we definitely have an overestimate. What can we do to get a more faithful representation of that area? Something a little closer.
Get the area of all these triangles and subtract it.
Okay, so I can represent all these as triangles and find that. Let's say I'm gonna be really close-minded about this though. I want to stick with rectangles. I don't want to deal with other shapes. I just want to deal in rectangles. Is there anything else I could do to make that area less of an overestimate?
Take, like, you can get more rectangles from the extra area, just subtract it.
I get more rectangles, right? So let's do this at least one more time. So we use 4 rectangles. Now we're going to use that 8 rectangles. Let's still stick with the paradigm that all our rectangles are going to be equally wide. So now, if I split this up into 8 equal pieces, how many different areas am I going to find now? So while I'm drawing, did we take what did we use for the height last time? Was it the right end of the rectangles or the left end? Right end. So how many areas do I have, or how many areas did I find last time on Wednesday?
4.
4. How many am I going to deal with now?
8.
Going to find 8 areas, right? Do we still agree that I'm going to have an overestimate?
Yes.
Is it going to be as much of an overestimate as last time?
No.
Why not?
It's getting to be more exact.
Right. So yeah, those white spaces there, I'm making those smaller. What if I were to use 16 rectangles? What would happen to my estimate then?
It'd be even closer.
It'd be even closer, right? It's still going to be an overestimate, but I'm getting even closer. So just to kind of give ourselves a benchmark, I'll write down 15 over 32 because that was our area when we did 4 rectangles. So now I'm going to find 8 areas. Let's find those. So let's start on the left-hand side. I want to find the area of this rectangle here. I'll call it A1. Let's find that one, and then we'll generalize it to get the other 8 or the other 7. How would I find the area of that rectangle there? How do you find the area of any rectangle? Let's start with that. Length and width. I'm going to call this height and width because just to make it clear what side is which. What is the width of that rectangle? Horizontally speaking. 1/8, right? Is that going to be true for all these rectangles?
Yeah.
Okay. So the height, or sorry, the width is 1/8. What is the height going to be?
Oh, I need to move next square. Well, the height of the first one's going to be 164.
How'd you get that?
Plug that in that value because it's the X value, plug it into the equation.
Right. So just to show where everything's coming from, I'll represent like that. And I'll leave it unsimplified. I think that's going to just make it easier to deal with at the end. If that is how I find the area of the first rectangle, what's the area of the second rectangle going to be? The one just to its right.
Times 2/8 squared.
1/8. So why did one of these things change and the other one didn't?
Because the X is now double the length.
Right.
even though,
The X is double the length?
well, the X value, when you're plugging it into Y equals X squared.
Okay, so let's be really clear about something. So we're multiplying height times width, right?
The height.
So which one of these dimensions changed?
The height.
The height, right? So the height is coming from what?
Well, now it's gonna be X 2/8. So like, you're gonna put X is equal to 2/8, and then you square that instead.
I didn't even write down what you said.
Yes.
Yeah, it was a 2/8 squared, right?
Mhm.
Okay,
So is that because the X coordinate is 2/8?
right, that's what I was getting at. How are we getting the heights of all these rectangles? Like, what's governing that? How am I picking those
The
heights?
equation. Y
Comes
equals-
from, basically, it comes from the curve, right? So, and one more thing I'll highlight here, and by the way, I'm picking the right ends of these rectangles just because I want us to have something consistent to shoot for. I could really pick anything on these intervals, we'll talk about that later, but yeah, if I am picking the right-hand side of these intervals, then the place, the first height is gonna come from the X value of 1/8. And the height is gonna come from E squared. And the next one, 2/8 squared, and so on, right? Any questions there? So can I generalize this then? What are the next several of these things gonna look like?
1/8 times 3/8 squared.
Right. So if we do this, so we said we're gonna get a better estimate, right? But at what cost? What am I, like, what penalty am I paying for getting a better estimate? More work, right? I have to do more calculations. And that's kind of the trade-off here. If I want a better estimate, I basically have to do more for it. And I don't think I left myself enough room. 1, 2, 3, 4. Yeah, so we got those 8 rectangles now, right? Any questions about how we got those? Solomon?
Not a question, but is there, I'm assuming there's like some form of an equation somewhere we wouldn't have to do this whole thing manually.
You hope so, right?
Yeah.
Yeah. So we're working up to something. But it's gonna look mysterious if we don't kind of build up to it. So are we okay with the rationale here? So basically, I want to find the area of a thing that is very not smooth. I mean, it is a smooth curve, but it's like using rectangles is, you know, hopefully it feels a little suspect, especially the fact that I'm choosing only some, like, to use some of them. So what we're working up toward is, how are we going to get better and better estimates? What are we doing with the number of rectangles? We're increasing them, right? So let's try to generalize this first. Now, you know, I had 4 rectangles, I had 8 rectangles. Now I want to just have, I'm going to call it n, some general number. So basically, same general rationale. So basically, I'm taking that X interval from 0 to 1, I'm chopping it up into a whole bunch of pieces. I'm going to use the right-hand side of the interval to tell me how tall those rectangles are. I'm going to find all those areas, I'm going to add them up. So let's do this now. Let's find the first few rectangles and see if we can generalize from there. Again, area is equal to width times height. What's the width of the first rectangle?
Right.
Not anymore. I'm no longer dealing with 8 rectangles, right?
So n over 8,
Where's the 8 coming from?
the amount of divisions we had.
Right, but also we're throwing away the 8 rectangles thing.
Width equals X.
The width equals what?
X.
Okay, let's think about it. So basically, how wide is the total area that I want to find? 1, right? So that's the total width, right? So let's do this.
1 divided by.
I'm going to say, we'll call this delta X because we're going to use this later. You said 1 is the width of the entire interval, right? How'd you get that?
The width is 1, 1, 1, so width is 1. the max, like the whole thing is just one.
Right.
value.
Okay, just to be clear, you pointed, so you call this coordinate 1, 1. Do both of those values of 1 matter to you? For what I'm asking?
With no,
No, okay, which one does?
the first one's X.
Right, so the interval, the rightmost x value is 1, the leftmost is 0. But now I want to divide those up equally over a certain number of rectangles. How many rectangles is that for me? N, right? So I am not telling you what N is, we're trying to generalize it, but we can say the width for any one of these things is 1 over N, right? So I can apply that to all of these or all these rectangles I'm about to deal with. They're all going to have a width of 1 over N. How about the height? Is that going to stay constant from rectangle to rectangle?
No, it's double.
So let's do this. Let's just find the first height. Let's find as many heights as we need to before a pattern jumps out of this. This first rectangle right here is a little tiny one. Has a width of 1 over N, right? I am using the right end of these rectangles to figure out, so basically to sample my function to get its heights. So what is the x coordinate of the right end of that first rectangle? Maybe I should ask this first, what's the left end? What's the left x value?
0, 0.
0, right? Should just be the left end of the entire interval. And then I'm going to move to the right by so far. What is this point right here? What's this x value? One over N, right? Okay. That's a big thing that we have to got to get our heads around before we can go really that much further. So are we okay with why that first x value is 1 over N? In this case, it really comes down to how wide is that first rectangle. So our first x value is 1 over N. How am I going to get the height then? 1 over N squared, right? We're applying the function to that. So this next x value for the second rectangle, what is that x coordinate going to be?
Oh, 1 over N cubed and then 1 over N to the power 4.
How are you getting your increased powers?
Because you're adding 1 over N to every instance of the rectangle now.
So what? So you're adding. I'm adding 1 over N to something each time. What am I adding 1 over N to? To itself, right? So let's start small. This first rectangle had a right endpoint of 1 over N. What's the next rectangle going to have a right endpoint of 2 over N? So this x value is 2 over N. You said this next height would be N cubed. You still agree with that?
No.
What do you think now?
It's going to be 1 over N.
It's gonna be 2 over N squared.
2 over N squared, right? So remember, the way I get the y values is from, I figure out where the x value is, and then I let the function tell me what the y value that goes with this. Do we think the third one's going to follow a pattern of some kind? So what do you think the third one's going to be? Are we convinced of that, or are we just hoping?
I'm convinced.
Okay. Anybody else think we're just latching onto something too early? We can go with this. I mean, that's part of the rationale for making all these rectangles equally wide. This distance is 1 over N. This distance is 1 over N plus 1 over N, and so on. So yes, these should all be spaced 1 over N apart, which is another reason why this thing is called delta X. What is delta? What's the capital letter delta mean in math or science or change, right? So each new rectangle I am changing by this thing, 1 over N. So I can absolutely generalize and ... right? All the way up to the last one, which is going to be what? 8?
Or N over N.
You're stuck on 8. Right. So yeah, the last one is the nth rectangle, right? The whole reason we're doing this is I don't have to decide how many rectangles there are. I can do a thing and figure out what it is later. This will work for all those cases. So I have a bunch of areas. I didn't write all of them down, but I have a bunch of areas, right? So now I want to add those things together. So have we seen this thing before? Okay, so for those of you who haven't, this is capital letter sigma. Basically, this thing gets used in math when you're adding up a bunch. It's the sum of, you're adding a bunch of stuff. So kind of walk you through the notation here. Don't want to call it n. So bringing in this new letter I. Basically what this is called is the index of this summation. I'm going to start counting at 1. I'm going to count all the way up to the thing that's on top of the sigma, which is n. So can I generalize all the things I'm adding over here?
Is that I equals 1?
I equals 1. That tells me I is what's called the index. Basically, it's the variable in this notation. So where do I start counting and how far do I go? So if I would have done one of these sigmas for the last example, that would have been I equals 1, and then on top of what it said 8. This time it says n because I want this thing to be fungible so I can deal with it later. Can I generalize? So look at the first 4 rectangles we came up with. Can I generalize that so I can say this? So actually I can like come up with a formula for some term in here. Let's start with this. Is there something that just never changes from one term to the next?
The denominator's N.
Maybe I'm not being clear here. So as we go from A to 1, basically these are 1, 2, 3, and 4. These are the I values. So as I changes, is there something that just never changes over here with these the way we found these areas?
They're always getting squared.
They're always getting squared, so I can deal with that. I'm squaring something, right? Is the thing I'm squaring changing?
Yes.
Okay, so when I equals 1, what's inside this bracket?
4 over N.
When I is equal to 2, what's inside this bracket?
2 over
Okay, so can I generalize that in a certain way? If I is equal to, if it's the 9th rectangle,
N. Oh, I over N.
right, it's I over n, right? So my heights are going to come from, or let's back up even one step back. My x values are going to come from whatever the I value is and dividing that by n, the number of rectangles there are. That's the x coordinate, and then the way I'm going to get the y coordinate is by squaring that. All right, but I'm missing something from there.
And then it's times I over N.
Is it times I over n?
So that's always 1 over N.
It's always 1 over n, right? So my area here is going to be equal to this. Isabel, to answer your question, so if we're looking at 0.22 on the graph, for example, would the index then be I equals 2? Basically, the index, that's going to be governed by how wide the interval is, and we'll see an example of that as we, once we get into a different book. But for now, any questions on how we got this area? Okay. I'm going to do one more thing to simplify before we go. So this is equal to the sum from I equals 1 to n of I squared over n cubed. You okay with that?
I squared over N cubed.
Yes, is that clear why?
Yes, yeah,
Okay.
yeah.
N squared here, into the first here. All right, any question here? All right, so let's do something with that. So we have just found this. The area is equal to this sum from I equals 1 to n of I squared over n cubed, right? These areas are always going to be wrong, right? No matter what n I choose, the area is going to be wrong. But what's the way to get the best possible area? What do I want to do with n?
Highest number possible.
Highest number, what is the highest number?
Infinity.
That's not a number. But is there a way I can see what happens as n gets really, really big? I can set a limit to this, right? So I want to limit this somehow. And so I want to limit, and I want what to go to what to really investigate this. I want n to get arbitrarily large. So basically I'm taking my sum that we dealt with, and instead of picking really big values at n and seeing what my area does, now I'm going to see what happens as n gets really, really, really big. So let's talk about how to deal with this. This thing right here is dealing with n getting very, very big, right? But the summation itself, what's the actual variable inside this summation, the way it's written? What actually changes? I. Okay, I changes. What about n? Just as far as the summation is concerned. No. N is just some number, right? It's just something like, I could say n is equal to 8, and I would vary I 1, 2, 3, 4 all the way up to 8. But the 8 just tells me when to stop. So because of that, I'm going to rewrite this like this. The limit as n goes to infinity of 1 over n cubed times this summation. I equals 1 to n of I squared. So basically what this summation is doing now, I'm going to take the first n square numbers and add them up, right? 1 plus 4 plus 9 plus 16 plus 25, and add those all together, right? If that's not clear, let's talk about it again. So let's just go through what this notation means. This Greek letter capital sigma means I'm going to, pretty much by convention, I'm going to add up a lot of things. I'm going to add up a list of numbers. I'm going to start with I equaling 1, so let's do that. When I is equal to 1, what's this thing equal to? 1. Okay, so I'm going to add 1 to something. When I is equal to 2, what's this thing equal to? 4. And so 1 plus 4 plus 9.
Okay, so the thing under capital sigma means that's where you start.
Let me give you a concrete example. Let's say that this summation was from I equals 1 to n equals 5. Of I squared, and this would be equal to 1 plus 4 plus 9 plus 16 plus 25 and no further. So yeah, a summation, the way it's written like that, it terminates. It has a set number of things that you're going to add together.
So for n goes up, is I always going to be 1?
You can say I equals whatever. It's commonly 1, sometimes it's 0, but you can set that starting index at whatever you like. All right, so any questions about basically what this notation does? Okay. This next thing I'm going to do, I'm going to ask you to take on faith. And I hope that's okay with you. I know that, or I don't personally know, someone discovered this, that when you add the first n square numbers together, it's equivalent to this. Oh, I knew I was going to forget it when we got here. N times n plus 1 times 2n plus 1 all over 6. So that's something that was discovered long ago. I believe I can prove this to you. I don't think it's really worth the time it would take to prove it. So I'm going to ask you to take it on faith that when I add the first n perfect square numbers together, this is the sum. I hope you're okay with that. All right, so from there, is that limit something I can handle? So one thing I see right away is that this happens, so let's keep diving into this limit. The limit as n goes to infinity of, y'all mind if I distribute? Okay, let's do 2n squared plus n plus 2n plus 3n plus 1 over 6n squared. What do we think about this limit here? Do we have suspicions?
You can't factor
Can't factor it, no, but we can still get to the end of it. It's been a while, but what do we remember about dealing with limits like this? Rational functions.
Oh, it's the denominator, right?
Yeah,
We go what?
You just look at the denominator.
At only the denominator?
no, because it's n squared and n squared on both, it's gonna be 2/6
Okay, so
or 1/3.
yeah, so let's do this. Basically, to make it more clear, I'm going to divide both numerator and denominator by n squared, and then I get this limit. The limit as n goes to infinity of 2 plus 3 over n plus 1 over n squared all over 6 to the n squared. No. Over 6. So what happens to that limit? What happens to those two terms as n gets really, really large? Smaller and smaller to some limit, or just
It's basically 0.
to 0, right? They go to 0. So because of that, this limit's 2/6 or 1/3. So the area underneath that parabola over that interval is 1/3. That's what let's kind of recap the whole thing. This weird summation that I started this slide with, where did this come from? Like, what was I doing?
Summation of the rectangles.
I was adding a bunch of rectangles, and I was using those rectangles to stand in for like little sub areas on that graph. So a lot of you told me that the more rectangles I have, the closer I have to being true about what the area is. If I can possibly see, if I can look at what happens as there are infinitely many rectangles, I get an area of 1/3, which is exactly what that area is. It's kind of a big idea, so, okay, Gary, yes it does. So, ask me questions, we got plenty of time to talk about this. This is a pretty big thing.
Where did you plug it in? Wait, so what area was it for? The first one, the second?
Yes. So here's the thing, we were dealing with the same area every time, right?
Oh, yeah.
So what was changing between, like, so we kind of looked at this 3 different times. What was changing every time?
The amount of rectangles.
Right, but it was the same function, same closed interval, right?
So like what values did you plug in for n? Like when was the value for n plugged in? Like,
When?
yeah.
Right at the very end when I stopped writing the limit operator. So I mean, we didn't really evaluate n until the very end.
Oh, okay. So is that the function for area then? The limit of n approach infinity of the 2 plus 3 over n plus 1 over n?
So the area of what?
Of
Of any function or this one?
was it just on intervals?
Of any interval? What's an interval? I haven't really talked about what an interval is yet. So this thing right here we did, let's talk about like what that we did is only effective for the function I'm talking about.
1 over n squared when you multiply the top and bottom?
I think a better way to ask that.
Oh no, when you multiply by 1 over n?
So why don't we do this? Why don't we back up a slide? how do we deal with this area? So I wanted to find the area under this curve, that blue shaded area. How did I find the area there?
Splitting up into rectangles.
So I took the shaded region, I split it up into rectangles, found their widths and heights, found all those areas and added them together. I did that for this function.
Would it depend on what?
Could you do that for other functions?
Yeah.
Okay, so let's look at the way we found these. We call these widths 1 over n, right? Would the width always be 1 over n?
No, because it could be, depending on the.
Yeah, this thing could be wider, right?
Okay, gotcha. Yeah.
Or it could go from 1 to 2.
Mhm.
In which case, I think these widths would still be like 1 over n, but I think these x coordinates would be different to functions. So all of these areas right here are just rectangles, right? Could I take other functions and think of them as rectangles and do this again? So the process is generalizable, but everything we've done.
Is just for this.
Yeah, so that area 1/3.
Is for y over.
That is for this parabola on that interval. So if we did some other function from 0 to 1, you'd have a different area problem. If you did the same function from 1 to 2, the area would not be 1/3.
But
So-
these are the steps.
Yeah, me and Will, yeah, this is, I'm gonna focus on the rationale more than the steps. And really, the really brute force kind of like, at this stage, clumsy thing we did, we took something that was very not rectangular and made it rectangular so we could talk about its area. And you can do that with lots of functions, not just this one. But before we generalize that, I want to make sure that we're happy with the rationale.
So that first area function, the one at the very top, that's not true for every interval.
No, it's not. So yeah, the fact that I'm summing up all these I squareds over n cubed, that was directly a result from the fact that we were dealing with that parabola over 0 to 1. And maybe that'll become clear as we look at some more examples. So let me basically put some formality behind what we did. We're finding the area of some region. So let me draw you a picture. And this time I'll draw it in a general way. So let's say from A to B, not necessarily. So I have some function. Oh my gosh, stop hitting the button. So I'm trying to find that area. Call that region S. So under the graph, the thing that we're talking about you can do for functions that are not continuous, but we're going to stick with continuous functions for the rest of the semester. Basically, it's the limit of the sum of areas of rectangles. So if we kind of try to boil down the process that we just went through, we started with a few rectangles, then did more rectangles, then tried to look at what's going to happen as you start talking about arbitrarily many rectangles. So even though this curve I drew you is decidedly not straight, I mean, I can think of it as rectangles and just keep subdividing those rectangles and get better and better estimates. So here is essentially what we've done. So this capital R, this process, and we'll talk more about it later, this process is called Riemann summations. He's the mathematician who formalized it, is basically taking a function, splitting it up into this idea of rectangular areas and adding them all together. And if you look at basically inside these square brackets here, this is essentially what we did for our rectangles, right? How do we find this delta x? Why don't we do this? How would I find delta x for this generic thing that I drew up here? Assuming I want to make all my rectangles the same size, the same width. How would I find that delta x for any one of them?
S over N.
How would I find the width of the whole region? Or S is just the name. What things would actually have numbers if I was being specific?
A and B.
A and B, right? So how would I find the width based on A and B?
B minus A.
B minus A, right? So the full width is B minus A. And how many times am I subdividing that B minus A?
N.
N times, right? So that we're going to try to hold constant. We're going to try to keep all of the widths equal. So delta x is really the width. F of x sub 1 star. What is that going to give you? Maybe I should unpack what the star means there. So basically what the star represents is that these little subintervals are going to have many, many points in them, right? The star just means you pick one. So for everything we've done so far, I picked the right end of an endpoint. That's totally arbitrary. You could pick wherever you want.
As long as it's consistent.
No, you pick wherever you want.
No, yeah, but for that specific problem, you have to keep that. No?
I could pick the right end point of this rectangle and then the left of the next one in the middle. Yeah, it would, so you can do those things. It's about coulda, not shoulda. There's no reason to do, you would do something weird like that, but you absolutely could. Maybe I want to find the highest estimate, so I grab the highest point in the rear, on the rear, things like that. But this right here is a y value, right? F of xi. So basically what you're doing here is this is not written in sigma notation, but this is that sum. I am taking the area of a rectangle and then the area of another one, and so on and so on and so on, and adding them all up. And then I finish that process by seeing what happens when the number of rectangles gets arbitrarily large. So a couple things I want to make sure we're okay on here. Do we know what this thing means? There's kind of there's some new language in here, there's some new notation. Are we okay with what this means? And additionally, do we see that this is really the same thing as what we did in the very last slide? Any questions before we use it again? Okay. So let's use a different function now. I want A to be the area underneath this graph, this function, f of x equals 2 plus cosine x. And I'm looking between x equals 0 and x equals pi. I want 4 rectangles. So let's do this twice, once with right endpoints, once with left endpoints. I'm trying to find an area, so let me just remind you of the thing we just talked about. This area is equal to, I'll use sigma notation this time, but you can use either one. Starting at I equals 1, what number should go on top of this sigma? I mean, I can always call it n, but do I know what n is? No. I should. N is the number of rectangles I'm going to make, right?
So pi, yeah.
No. 4. So what is pi? Like, what does pi represent in this case?
The right endpoint.
It's the right endpoint of the full interval. But that doesn't mean I have to make pi. How do you make pi things?
Would it be 4 or would it be pi minus 0 to find the width?
Yes.
Yeah.
But I'm asking. I asked how many rectangles are there.
Oh, how many? Okay.
So yeah, you're. What question were you answering?
I wasn't answering.
Okay. So there are 4 rectangles, right?
Yes.
How wide is each one?
Or pi, quarter, 1 over pi.
Pi over 4.
It's one of those things.
It's pi over 4.
Pi over 4? Okay, maybe we should draw a picture.
Wait, so how do we get 4 then? We just said 4?
Yeah, I told you 4 rectangles.
Wait,
Yeah, and the one in the first and second bullet.
Oh, okay. 4.
So I'm just gonna draw an arbitrary curve here because we're just kind of organizing. So this is our full area, right? Yes, the full width is pi. The width is pi, right? And if I'm making 4 rectangles of equal width, how wide is each one?
Pi over 4.
Pi over 4. So that kind of gives us one of our parameters we're going to deal with. Delta x is equal to pi minus 0 over 4, which is equal to pi over 4. All right, so that's a big piece we need for this sum that we're going to deal with. What else do we need to start estimating this area? I need heights, right? How many heights? I need 4 heights, right? So that means I need a bunch of x values. So let's get those first, because I can't get a height unless I know like where to ask this function what the height is. Whoa. So you first thing you said was pi over 4?
Yeah.
How'd you do that?
That's just when you plug it into this. Wait, oh, don't you have to plug it into the function?
What am I asking for so far? I just asked for the x values.
Yeah. So you were right.
So you're good. I mean, let's go slow. We really need to be sure about. So I'll ask this one more time. Where do the heights come from? How do we get them?
From plugging in the x.
From plugging the x value into the function, right? So I think the most important thing is to make sure you know what x values matter. And I believe these are the ones that matter for the first bullet, right? So if x1 is equal to pi over 4, what does that mean about f of x1? Should be 2 plus cosine pi over 4, which is 2 plus cosine pi over 2, which is 2. And f of x3, which is equal to, let's do some abbreviating, 2 plus cosine 3 pi over 4, which is going to be 2 minus radical 2 over 2. And then 2 plus cosine pi will be 1. So I have my 4 heights now, right? Do I have enough to get an area?
Yes.
Cool. How would I do it?
With 5 height.
Time, yeah, multiply the width by the height, right?
And then
What's the width?
Width is the first one. It's that x value.
Oh, it's pi over 4.
The width is pi over 4, right? So remember, the width is not variable, right? But that is a common mistake, and I always ask the question, if you're letting the width vary, that means you're telling me a rectangle gets bigger when you move it around. So yeah, the width should be a constant thing. I'm going to multiply all my heights by my width, right? So this area should be, basically what I'm doing is basically I'm factoring out the width, and that'll be this is my collection of heights, right? And let me underline them to keep them separate. First rectangle, second rectangle, third rectangle, fourth rectangle. We okay with that? So that should come out to be 7 pi over 4.
Why is that multiplied by pi over 4?
Good question. Why is that multiplied by pi over 4?
So that's the width.
That's the width, right? So I took a shortcut for real estate's sake here. What am I really adding up to find this overall area?
All 4 areas.
All 4 areas, right? And how do I find any one area?
And multiplying the width by the individual height.
So
that you just, yeah.
width times height plus width times height. I just factored it out to save some room. So that is the area if we use the right endpoints, right? Clearly don't have enough room, probably more time to figure out what the area would be if we did the left endpoints, but I do want to talk about what would change. So let's just kind of relitigate the whole process for the left endpoints. We said 4 rectangles, is that going to be the same?
Mhm.
We said delta x is pi over 4. That's still going to be the same.
Yeah.
Okay. Yep. Same width, same number of rectangles. X sub 1, we said was pi over 4. Is that still going to hold?
I mean, those all x values are going to change.
What would the first one be?
That was left.
You're going to the left endpoint, right? So
First one.
I think I heard a 0 out there. So let me just make a little box here to show basically where the paths diverge, but the first x value, x1 is going to be 0.
The second one's
So hopefully that this makes it more clear that when you're doing this, I mean, if you were getting something exact, then it wouldn't matter how you did it. But the fact that you can sample different places and get a totally different area means that we're introducing some error here. So yeah, basically just do x values, you have to find new heights, right? Or one new height. Any questions there? All right.
And then we would use this data to make a new equation.
What do you mean by new equation?
By new equation, I mean, like similar to the one we found for y equals x squared. With the integer of 1. Like similar to that. Or like, I mean, this question isn't asking for it, but like. That's
So remember,
what we're getting to.
let's think about the commonality between the parabola and this cosine wave here. Between how we found that area to this one, what do they have in common? That's it, right?
Yeah.
That simple idea of a rectangle, that is how we're doing all of these areas. And that's really what all these are, right?
Mhm.
Width, for the other one, the other width, it was 1 over n. This one we're calling pi over 4. How do we get these heights?
By plugging in the
By finding a list of x values and asking the function what height goes with those x values. So, yeah, could you do this for any continuous function at the root? So, I guess the last thing I want to ask is this. What modifications could we make to this thing right here to find this left-hand area? Because I think I could do it pretty easily. Am I really using 4 different rectangles to find the area using the left endpoints? No. How many rectangles am I going to reuse that I used from the last 3, right? The only one I'm going to have to change is what happens when x equals 0, and that would give us y equals 3. So that would give us a new area for that. Any questions here? All right, I'm gonna go ahead and stop here. We have one more thing to talk about with this section, but then we'll wrap that up. All right, I'll see you on Monday.